So, welcome everyone. We have last class we did something on Miller indices. So, we will continue our discussion on that. Two important results in Miller indices. One is that for cubic crystals, for cubic crystals see it is very important to know the plane normal. So, suppose we have a plane HKL. So, we want to know what is the direction which is normal to this plane. Now, for cubic this is very simple, because the plane HKL is always normal to the direction UVW. So, if direction is given, sorry, made a mistake here, direction HKL itself, direction HKL. So, same indices. So, nothing can be simpler than that. What is normal to 111 plane? The direction 111. What is a plane which is perpendicular to direction 110? The plane 110. So, they are mutually perpendicular, but we need a proof of that. So, we will give that proof, and the another important result is the Weiss-Jones law. Which we will see. So, let us try to look at these two things. So, first let us prove this property of cubic crystal, that the HKL direction is perpendicular to HKL plane. So, let us assume that we have a cubic crystal system. So, in this case the crystal coordinate system is very close to Cartesian coordinate system, although it is still not Cartesian, because crystal coordinate system is still the vectors are of length a. So, they are not unit vectors. So, these are the three basis vector, let us say. So, we know that a. So, if we want to write it in terms of the corresponding unit vectors, which are let us say I, j and k, that is your Cartesian system, then A is simply A times I, B is simply A times j. This is the simplicity of cubic, that although the vector is B at 90 degree to A, but length of that vector is same as that of the vector in the x direction. So, A, B and C are equal for cubic. Or you can say length of vector A, length of vector B and length of vector C all are equal, and we are calling that A. So, vector C also becomes A times k. Now, let us introduce our plane. So, let us say that this is our plane. This is the HKL plane, and we are looking for the normal to this plane. So, let us say that this is the normal, and we want to prove that this normal is also HKL direction, but currently we have not proved that. So, we can't assume it to be HKL. So, we give it a general designation UVW. Okay. So, that is our. So, UVW direction means in terms of vector, because UVW is the Miller indices of the direction, and the Miller indices of the directions are nothing but components with respect to the crystal basis, and the crystal basis is ABC. So, UVW vector UVW is nothing but U times A plus V times B plus W times C, which in the cubic case it reduces to U A times I plus V A times J plus W A times K. So, we have used already the cubic property both of equality of equality of the three lengths, that A, B and C are of equal length, and also their orthogonality, that A is parallel to I, B is parallel to J and C is parallel to K. So, we have used here using cubic properties. For other crystal systems you can't write this, you will be stuck with U A plus V B plus W C, because A, B, C are not equal, they are not necessarily orthogonal and so on. So, you can't write A in terms of I and B in terms of J and so on. So, this is our normal vector. So, let us give it this was the Miller indices of the normal vector. So, let us say that the normal vector is n. So, this is the vector n. I can't say that it is a unit vector. So, I am not using hat, I am simply using an arrow, but I know by assumption I know that this is a vector which I have assumed to be parallel to my plane HKL. Now, what does the definition of HKL tell you? That is the Miller indices of the plane. Yeah, Samyak? Here. Which one?
In this, the second equation, u a vector I cap is v vector d cap v vector cap. You underline them, they are not vectors.
Okay, sorry. Means the yeah, I was just emphasizing that they are equal. I was not saying that they are vector. Thank you for indicating that. So, and thanks for the eraser provided by the notebook. I can remove that. Okay. So, I was only underlining it while talking, but I was not saying that they are vector. They are scalars. Yes, A is a scalar. The length of. So, we have a cubic unit cell. So, maybe I should draw that. So, here means this is a magnified version where the cube is not shown, and the lengths, the three edges of the cube are A, and A. So, that is the lattice parameter. A is the lattice parameter. So, it is a scalar. Now, yes, now what can you say about HKL? So, what does HKL plane mean? By the very definition of Miller indices. reciprocal of intercepts. Yes. So, reciprocal of intercepts in terms of corresponding lattice parameters. What do we mean by that? We mean that H is the okay. So, we mean by so let us look at the intercepts. So, here is my origin and let us say OA is the intercept on in the x direction, OB is the intercept on the y direction and OC is the intercept in the z direction. So, this means H is representing OA. So, what exactly that means? That the vector intercept OA I can write as H was reciprocal of the intercept. So, reciprocal of H will be the intercept. So, reciprocal of H will be OA, but in terms of the corresponding lattice parameter. So, I have to multiply it by A. So, that will be the magnitude, or why complicate the writing, we can simply write OA as this, and which means if I want to write it in terms of vector, I can write it as OA is equal to 1 by H vector A, because OA is in the direction of the vector A along the x axis, and this will become in the cubic case, this will further simplify to A by H I, because A is A I. By the same token, by the same arguments, you can now write OB as A by K J and OC as A by L I j k, A by L k. They are totally different quantities. So, now let us see, let us recall that our plane was like this, our plane was A, B, C, and O was the origin, and I have developed now formulas for the vector OA, vector OB and vector OC. That means, it is easy for me now to write vector AB. Why I am interested in vector AB? Because vector AB lies in the plane, OA, OB and OC are not lying in the plane, and I want to explore the plane and I want to find two vectors in the plane. So, maybe AB and AC appear to be good choices for vector in the plane. So, AB becomes OB minus OA, which we have just seen. OB was A by K j minus OA was A by H I. Maybe it would have been better to avoid, means one way of avoiding this k interaction could have been to use E1, E2, E3 for the 3 basis vectors, then we would have been safe. So, but now we are into it, so let us not go back and revise that. Maybe in your notes later on when you are practicing it, you can use E1, E2, E3. In this course also we accept E1, E2, E3 notation also. So, both are acceptable. So, this is AB. So, we have found one vector in the plane. Let us find AC now, the other vector in the plane. So, that is OC minus OA. OC was A by L K minus A by H I K by L minus I by H. Now, I will use this. So, I have what we have done, let us see. So, we have done a very simple thing, that we have found a expression for the normal vector, a normal vector n, which we had here, here. So, that was simply A u y plus V j plus W k. Please remember that this is u, v and w is what we are unknown. We have assumed, and this is what we are trying to find. So, the problem is that HKL is given, HKL is known, we know this is the plane, and I am asking you to give me what is the direction normal to it. So, we have to find out UVW. So, the goal is to solve for UVW using the fact that the vector n is perpendicular to the plane, and since n is perpendicular to the plane, n will be perpendicular to both these directions. So, we can use the dot product condition. So, since n is perpendicular to AB, what do you get? You get A times UI, sorry, let us write that step also. So, that means n dot AB is 0, which will mean, which will give us n was A UI plus Vj plus Wk, and A was, AB was A times j dot k minus I dot h, and this is equal to 0, because the two vectors are normal. The plane normal is perpendicular to all the vectors in the plane. So, the plane normal is perpendicular to the vector AB. A are scalar, so we can cancel because the other side is 0. So, we can divide it by A square, and let us see other vectors. So, we will get, now I j k are orthonormal vectors. So, we know that we know that I dot j will be 0, j dot I will be 0, and so on. So, let us not write all the terms. We know that because of the orthogonality, again these are not to indicate that these are double vectors, already they have arrow above them or hats above them, but I was only trying to pinpoint. So, the only terms which will survive is I dot I, which is 1, and j dot j, which is 1. So, I dot I term is minus u by h I dot I, which will come from the first term of the first bracket multiplied by the second term of the second bracket, and then j dot j will come from second term of the first bracket, that is V by k, and this is equal to 0. other terms are anyway 0 when you expand this product out. Okay. So, we have u by h is equal to v by k. Now, similarly, you can apply the condition that n is perpendicular to AC. This will give you n dot AC is equal to 0, which is again A u I plus V j plus W k dot AC. Remember, we have found AC, k by L minus I by h, A times k by L minus I by h, and this is 0. Again, I dot I gives you A can be cancelled, I dot I gives you minus u by h again, and plus k dot k. So, here is k, so you will get W by L. W by L is equal to 0. This gives you u by h is equal to W by L. So, u by h is equal to V by k, u by h is equal to W by L. So, from 1 and 2 you can write to W by L. And since these are equal ratios, let us say that this equal ratio is something. Nice to use some fashionable Greek letter lambda, say. We have introduced, this is not a quantity which is defined, we are now defining it. We are saying that this equal ratio is lambda. So, then u is equal to, because we wanted to solve for u, v and w. So, that is why we called it that lambda. So, u is some lambda times h, lambda times h, v is lambda times k, w is lambda times L. So, essentially we have solved for u v w, except that we do not know lambda, but thankfully in crystallography you do not have to know lambda if you are trying to find out the Miller indices of a direction. Remember, we said that Miller indices of a direction can be defined by any vector, because 2 times or 3 times a given vector all will give us the same Miller indices. So, using that property, this lambda actually can be divided. So, we can divide by lambda. So, u v w becomes lambda h, lambda k, lambda L, and dividing by, we can say, we have said that we can divide by any constant factor. So, dividing by lambda we get h k L, and that is the beautiful result we were looking for. That is why cubic is so simple. So, u v w becomes h k L. But remember that this is for cubic only. In some other cases this can still be accidentally true, but you can't take it for guaranteed. So, suppose it was orthorhombic or tetragonal or orthorhombic, let us say A, B and C are not equal. Then along the x axis you have a direction 1 0 0, and this face of the crystal is again 1 0 0. So, here you are finding that 1 0 0 direction in orthorhombic also will be perpendicular to 1 0 0 plane, but this is limited to some such a special planes and a special direction. Arbitrarily if I see, so if so 1 0 0 direction perpendicular to 1 0 0 plane in orthorhombic also, but if I say 1 1 0, because of the inequality of the A and B, 1 1 0 will not be perpendicular to 1 1 0 plane, 1 1 0 direction. And keep remembering, if I make mistake, you can correct me also, and you can always be also alert that whenever we are writing direction, we are using a square bracket for direction, and whenever we are writing round bracket, we are using plane. So, it is not a general result, but for cubic it is always true. For cubic HKL direction, because we have proved it, HKL direction is always perpendicular to HKL plane.